Derivation of the first order rate constant equation. If we have a reactant A, and then it disintegrate or react to form product B, it shows that in the beginning we have A as a reactant. Think of cooking a soup with onion. Start with onions, tomatoes, and potatoes in a pot. As you apply heat, and the onions and potatoes and tomatoes start to disintegrate and then disappear. As they disappear, and that will be the reactant disappearing, making a new product, and the new product began to appear. So that will be the product. So you can say that's the product, that the soup, and the reactant. And basically the way we write the rate at which A is disappearing is called rate, which we then go to the rate constant and the concentration of A. But the rate itself is just describing how it's disappearing along here over time t. And we know that t equal to 0 there. So we can write the rate for A disappearing as difference in concentration of A, where D stands for difference, over difference in time, and that will be equal to, so that's actually equal, so equal sign there, so that will be equal to K concentration of A to power of 1. The power of 1 indicates the first order. If it's second order, it will be power of 2. The exponent will be 2. Exponent is power. As you can see, A is decreasing at the time t equal to 0. Let's say to about that point there, where at a particular time t. And as a result, so that will be A at the time t. And because it's decreasing, we have to put minus here. And the minus indicate that the value of A is decreasing. We could write the same reaction for the product. The rate of product will be equal to the K and with the concentration of B. And if you write here, it will be plus rather than minus, difference in concentration of V over time. So that will be plus. But because we creating the product, so it's an addition. And here we decreasing on A, the reactant is disappearing, so it's a takeaway. And we're going to basically integrate this rate equation, first order rate equation. We're going to integrate it. But before we integrate it, we need to rearrange it. And hence, what does the integration mean? Well, the integration is telling us that we're finding the area under we are finding all the total area of here that's been happening. So that's what we're trying to do. So integration is the area under the curve. And so to find the area under the curve of how much it's changing, the area under the curve would be to integrate. And before we can integrate, we have to basically rearrange this equation. I need to collect like terms. That means I need to multiply both sides by the t and divide both sides by concentration of A. And as you can see, this is over 1. Or we can just bring the concentration of A down and take the t up. So that's another way to do that. Okay. So we're going to write as minus the concentration of A over concentration of A will be equal to K dt. And then I need to multiply both sides by minus in order to make this positive. So I can then say the concentration of A over concentration of A will be equal to minus K dt. So what I can do now is basically that carry out my integration. And that integration will indicate that we're finding the area under that curve. So to do that, I need to write the integral, that's sum of the little rectangle. If you can form a rectangle like that. So that's what that meant. And then we form lots of rectangles like that, and that's what we're trying to do by adding all of them together. That means sum. And obviously that's the t here, that little change in time, and that's your concentration of A. So you can see, but in this case, to do this, I need to write that as from a time the concentration of A at 0 to concentration of A at a time t. So I can then say the A concentration of A over the concentration of A. So I'm just writing this one here. I'm just writing that one here. Will be equal to minus K times the integral of the t from t equal to 0 to a time t. But what I need to do to make this easier for me is to say, why don't I make concentration of A equals x? Then it's easier to do this properly. So I can then do integral at x naught and x to the power t dx over x, because concentration of A is x. So just replace that. And then that will be equal to minus k integral of 0 t dt. So as you can see, now it's easy to integrate this. But let's define few definition. If I have integral of 1 over x dx, that actually equals ln x. Also, if I have integral of, say, dx, that actually can be written as integral of x to the power of naught dx, which is integral of x plus c. How do I get that? Well, if I have integral of x to the power of n dx, that actually equals to x to the power of n plus 1 over n plus 1 plus c. As you can see, there's a 1 here, and I do know that x to the power of 1, x to the power 0 equals 1. So there's a 1 here, and so and I know the variable is x, so I can then say x to the power 0 here, because x to the power 0 is 1, because the variable is x. If the variable is t, then I'll say t to the power 0 dt. And that will give me, because when n equals 0, that'll be 0 plus 1, and that's 1. So, and that's 1. So that's why I get 1 here. 0 plus 1, that's 1. Well, what I meant is x to the power 0 dx will be x to the power 0 plus 1 over 0 plus 1 plus c, and that equals x to the power 1 over 1 plus c. So that's how we get that. So now we can do that for t. You can see that will be t to the power 0 because there's 1 here, and t to the power 0 is 1. So then I can apply the derivative, the integral of that. So to now do this one here, I can see that that would be, that integral would be ln, that's ln x, 1 over x dx, integral of that is ln x. So that would be ln x, and I'm integrated over x to the power 0 to x to the power x at the time t and x initial, because x0 is the initial value, and the initial value is the original value of a. So that will be the original value of a, they start with, and then start to decrease to a at the time t, which is less than a t is less than a naught. So don't forget x is concentration of a. And that will be equal to minus k, and integrating that, which is, you've already seen what that is. If that was t there and t there, I'll be getting t plus c. So that will be integral t plus c from 0 to t. So that means when t equal to 0 and when t equal to t. So as this is a definite integral, I can then see that this is going to be ln x subscript t minus ln x subscript 0 will be equal to minus k. Let's just put that into t plus, because that t equals t, c minus 0, t equal to 0, that'll be 0 plus c, close the bracket. Let's just bring this up down like that. So now we're going to get ln xt minus ln x naught equals minus, well, that's t plus c minus 0 minus c, which means plus c will cancel minus c, because that's minus times plus, that's minus. So we're going to get kt. Now this is the equation. This is the first order equation, first order rate equation, rate constant equation. So that's the equation we're looking for, really. But we can do a bit of manipulation a bit by basically rewriting that minus and turn that into plus. So multiply both sides by minus. So I get, so that'll be minus, that'll be plus, that'll be minus. That'll be minus, that'll be plus, that'll be plus. Because I'm multiplying both sides by minus 1. So we get ln x naught, right, minus ln xt, which equals to kt. So that's the another way of writing the equation. So that will be the first order rate constant equation. As you can see, what about if I'm dealing with a half-life situation where the half-life can describe what's going on when A decreases to half of its original value every time. But first, we could manipulate this equation and make it look nice by writing ln using logarithm function ln x naught over xt. That will be equal to kt. So that's another way of writing that equation. And we may be using this second way to describe the half-life. So what is half-life? Well, the half-life is the time taken, right? It's the time taken for the concentration of one of the reactant, or you must say the concentration of one of the reactant to reactants to fall or decrease to fall to half of its original value, or to fall to half its value, or to fall by half. Original value, so that would be the original value of A original, initial value, and this is the A in time t. Now if A is going to fall to half its original value, so we could rewrite this equation using that. So what we're saying is, when this is a x original and half of this x is going to be x. This is at t equal to 0 if you like. And at the time t of a half-life, that would be x naught over 2. So this is x naught at time t equal to 0, original value, initial time. And at the time t, we got the half of the original value. So this is called half-life. And that can be demonstrated from this graph here. But that the half-life will be when A equals to 0 and half of A. So if you look at that, that will be half of A there, roughly. So that will be A naught over 2. And so that will be the half-life. So that will be T half there. What about half of that one? So that will go like that. So that will be A naught over 4. So that will be T half again. What about half-life of that? That will be T half again, and that will be A naught over 8. So it's basically decreasing by half every time. But the exciting thing is that the time, the half-life time, are all the same value. So it's constant. So that's the same. So now what we need to do is use that by basically replacing the x naught, xt, by x naught over 2. So we have ln x naught over x at the time t, and when x at the time t is, well, we know that that's basically kt. So at x at the time t, we could have ln x naught over x naught over 2, because xt is now x naught over 2, and that will become k t of half-life. So when it gets to half its original value, the time it gets to half of its original value. You can see the x naught will cancel each other. And so we're going to get ln 1 over 1 over 2. And that equals k t a half. So we know what that is. We know that 1 over 1 over a is basically a. So therefore, we can write that ln, that will be 1 over 1 over 2. That's the reciprocal of a half. That would be 2. And that equals k t a half. And that's the equation for half life. That means the equation we can use. You can see it does not depend on the concentration because the concentration is not there. Here, you can rewrite that using the concentration. So you can see you could write that equation again here by just calling that as ln concentration of A naught over AT concentration equals to KT. So that's another way of writing that. Or you could use any one of these, whichever way you like it. Don't forget that the A, concentration of A equals X. So that'll be ln X. So that'll be ln A naught, concentration of A naught minus ln concentration of AT there, equals to KT.